Good morning, good afternoon, everyone. Today we have the episode of Coffee and Compressed Air, already 38. And today will be a little bit more technical. So you see me, I'm Elvira, and CTO of Direktin. Usually we have this show also with Dani. And whenever you see my face, you know that it's probably going to be a little bit more technical today. What I wanted to discuss with you, and also very happy to open to your questions, suggestions, and recommendations. So first of all, please grab the cup of coffee. It's Friday. Weekends are coming. And today I would like to discuss with you the baseline for assessment for audits and the savings for the compressed air systems. I know that it's been already 1 million posts, 1 million comments and discussions. And today I will maybe tell an extremely obvious thing, but I would like always to remind you about this. And I also would like to show you a very, very simple tool that you can use to calculate the baseline. You don't have to be the engineer for this. You don't have to, you can be energy manager, you can be person. If you're familiar with Excel, it's already good enough. But the whole idea of seeing the potential savings and pitching the project for the financial team, for the procurement team, or if you're auditor, you're pitching it also to your clients, and you collect a little bit of the data on the compressor room and others. I would like to discuss with you how exactly the baseline should be actually done. Why I decided to discuss this? Simply because I posted this week about the heat recovery, and I got so many comments that it's really insane. And there were so many comments that actually were very extremely different. So what exactly was the post about? The post about was that the heat recovery, if you see somewhere that as the heat recovery is 90%, 99% of compressor energy, that you use 1% of the energy for pressurized flow, and then you have 90% or 99% or 80% or 70% as the heat recovery. So I would like to make here a small remark, and actually will dedicate next week explaining, and I also explain this, what's the difference between the compressor, and if we take the heat pump or we take the boilers, for example, that create heat that you used for heating. Why you cannot just simply say this is like my 100 kilowatt, let's say, hour of my compressor, 90%, 90 kilowatt is will be used for heat. So this is my heat. This doesn't work that way. Thermodynamically, it doesn't work this way, and this is the whole topic about this. Also, from the cost perspective, if it doesn't work this way, I don't say that the heat recovery is not important. What I'm just trying to say, it's extremely important, and the heat recovery always should be done in all projects, and all the energy should be used. But the quality of energy and quantity of energy, it's a completely different thing. So we have a compressor. Compressor works for pressurize the flow, and then we have so electric energy is transformed into the pressurized flow, and the loss of this transformation is heat. And what we do, we recover this heat only for warming processes. It means that these kilowatt hours that are recovered, it's not the electric energy of the compressors, because sometimes you can see the claims on the internet, it's 90%, it's 150%, it's 200%. So the economics doesn't work this way. You recover part of this for the heating processes, but you cannot compare the kilowatt hours of the electrical energy to kilowatt hours of heat. So it is two completely different entities, two completely different physical things, and it's also completely different cost. Because if you take, for example, a heat pump, if you compare it to the heat pump, you don't have efficiency of 200% of the heat pump. You have a coefficient of performance, right? So, and it can be 2, it can be 1.5, but it's not 150% of the efficiency. It's just meaning that it just moves, the heat pump moves the heat out of the atmosphere, and then it moves inside the place that we need to heat it up. In terms of the compressor, we have electrical energy. We as a heat pump, as the heater, compressor is extremely inefficient thing. So device, because you get the very high quality, I call it like organized energy, electrical energy, and then you transform it into the basically waste, because heat cannot be transformed into any other forms of energy. So, and this is why it's extremely important to know when we do the baseline assessments, and in general, that we cannot just get 100 kilowatt and recover 90% of this kilowatt hours, and recover 90% of this, and recover 90 of them. And it will be heat, and then put the calculations on it, because simply even the 1 kilowatt hour of heat is costing less in general than the compressor 1 kilowatt hour. So it's two completely different things. So this is why when we have the, and I call it probably also some other engineers, you use a C&CA diagram, so you can use also the cascade diagrams when you quantify possible energy savings. A lot of the time I see that it starts with the compressor. Of course, it's correct, it's a generation, and then it's exactly calculates there, okay, what if I swap the compressor there, I do the heat recovery there, and what is going to be the consumption there. So first thing, that point that we already established, that we divide that the heat recovery doesn't go directly into the electrical energy. Otherwise, you get the efficiency there 100 or more than 100%. And you can, if you say to engineers or energy managers of the efficiency more than 100%, of course, you will be rather laughed at. So, because then we will have the perpetuum mobile. But of course, it's extremely important. So we always need to consider this, but we need to add it as the separate point. So we start with the total energy consumption of our compressor room, and then we can already see first what we can do on the demand side, what we can do on distributions, and what we can do. For example, if we identified also there are some leaks, so want to offer the leak services. So the company, if you're an energy manager, you want to get the leaks, you can see how much actually energy you can save from the electrical power from the compressor room, and then size correctly or run correctly your compressor room with the less energy intake. And then based on this new baseline from the reduction of the demand side, we already can see the heat recovery. And I want to show you now, I'm going to show you the screen. Let me just share it. And you can also try it yourself. So probably see now my screen. Hope so. So what I actually wanted to show, and please feel free if you have also any questions or any comments. So when we analyze the baseline, here you can see the electric saved from the compressor room. Here you also can see the demand side, so any additional savings on the demand side. And then here I think I don't have do I have a heat recovery, but you also can add the heat recovery and have a various topics. So let me just see if my screen is shared. I don't think so. Let me go once again. Just share it. And I'm going to show you this. Okay, I think now it should really work. And here, so, okay, so basically, we always start in our baseline with the compressor room. And here, for example, you see the compressor fleet. There is also another tool that you can use, but you also can just start here from scratch. It is the compressor. You can here open compressor room, add more machines. And I feel like that my screen is not shared, and that can be the problem. Okay, let me just try once again, because I follow myself also on LinkedIn and I don't see that the screen is shared. You can send me also some hands up of the, okay, let me try this. Let me try again with them. Okay, add to stage. Sorry. Okay, now it should be there. Okay, so a little bit of Friday frictions in our session. So once again, the baseline usually that we start is the installed power. It is then the calculation of compressed air energy. Of course, you can have the installation power, but you also can have the annual electricity cost. You also actually can add the measurement file, so the CSV file or Excel file, in order to get the real load profile for your compressor fleet. So here I just added the compressors that are really installed in the facility. And we have here 4 compressors, not advertisement of any of the compressor brand. So it is simply what you can, what the user here put in the compressor room. And other operating parameters that are extremely important, it is exactly for the heat recovery. So in order that if you're going to use your heat recovery, heat of the compressor for the water, for the boilers, or for anything else, you actually can check the demand for the boilers and the gas cost and other electricity cost in order to get to the savings. So here you can, and then how the entire idea, as I told you before, is extremely important that we start from the elimination of the demand side. So demand side, the most simple thing, it is the leak elimination, right? In case we identify the leak volume, or we usually in the facility where only once a year the leak detection is done, we can say 22% of the leaks are present in our facility. And of course, we cannot repair anything, so we will repair only 65. And then what is going to be the capex, and what is going to be the that, for example, includes ultrasonic leak detection, leak repair, or anything else. So you can simply add here another capex. So, and you can delete it, and then calculate this is the marginal cascade from the electrical energy. So meaning that I take the full electricity cost here, convert it into the flow that I have, and then I calculate also what happened if I remove some percentage, 10% of this. Again, it's very simple. It's only for the first estimation, but it also can help during the walkthrough of the facility through the audit for energy managers or maintenance managers, if you already see what are the problems, for example, in the facility. You can add a new lever here. For example, it can be some no loss condensate drains, some pneumatic replacement, demand reduction, something that you estimate like a 5%. Predictive maintenance, anything else custom. So again, it's also for all your imagination that you can use here. Then, for example, it can be control and sequencing output already for the compressor when the demand side is analyzed. Then we add the generation, and here you can add also the master slaves, local cascade, or any other savings. And here it's again important always to remember the mistake that I very often see is that we have an amazing equipment, for example, for the demand side. It is, let's say, one efficient cylinder, or it one efficient nozzle, or it is a vacuum pump instead of the using the vacuum ejector, or anything else. So a very good, efficient device. And of course, it will claim that it saves 50% of energy, and it does save 50% of energy, but it saves not the 50% of energy only for this certain operation. So meaning that at the end, if you have a 50% saved for this operation and you have 100 operation like that, maybe it's going to be just 0.5% of the final energy that you can save, but you still need to adapt your control sequencing optimization. You still need to adapt the supply side. Of course, I exaggerate here so that but if we need to adapt the demand side, we also need to adapt the supply side. And this is why it's extremely hard to fall into this 50% savings, 30% savings, especially also for the compressor room, because control and sequence and optimization, any monitoring, any predictive maintenance should be always done when we're sure that the air is used in the correct way. Unfortunately, I saw recently the projects where we have where the compressor was working just to blow off air in the atmosphere. So basically, it was some. Of course, I'm joking, but like not joking actually. So there are open pipes, and they are simply cooling or cleaning one piece of metal. Very often we find this application in the metal manufacturing, and you have a huge compressors working for the air, basically just to dump air in the atmosphere. In this case, you could simply install the blower if there are no additional pneumatic equipment is installed, or really put engineering nozzles, for example, right? If there are more processes, of course, there. So this is why it's extremely important to have this cascade logic and not just not simply provide some Excel tables to the energy managers, knowing that at the end it's not going to be the savings that are promised, and that's okay. It's really, I think, amazing results if you can achieve 20%, 30% of savings, 10% even. So, and then here you can switch on the compressor heat recovery, and this already you see the category is already from the heat recovery. So meaning that we actually can see the recovery factor. So we get the amount of the energy that can be recovered again from this from the compressor, and it's not the electrical energy that we are calculating here. So, but then we can see the what is the capex, the storage tanks, the sizings, some certificates, and so on. And of course, usually the heat recovery has a higher will result in a higher payback. So if you see here, the payback changes very, very significant. And again, what I just want to show you here, that it's an extremely simple calculation here for the heat recovery, but it's important to always consider this. But it's also important to remember that what is going to be the real savings here. You will always have the demand side savings, the electrical part savings, and you also will have the thermal savings, what is extremely, extremely important. So we need to work here on the logic that we start with the baseline, from the compressor room, we see at the same time what is the demand side, and then we polish everything at the end with the heat recovery. Because sometimes when we have a very small facility, for example, here you see the annual electric cost, they are quite small, so it's not a very big consumption of the compressor, so it's some small food manufacturer. So maybe if the payback is not right, good now for the heat recovery, we actually can work more on the demand side, on the pressure reduction levels, on the sequencing of the compressors, and so on and so on. Monitoring of the leaks and repairing of the service, rather than going directly to the heat recovery without doing anything on the demand side. Of course, when we go further in the bigger manufacturers and more demanding processes, high pressure manufacturers where we have a higher capacity of the compressor room, then we need to have the payback will go definitely like below 2 years. So I hope that I could give you a little bit of the overview and answer some questions on the hot topic that I got this week. I'm going to post, I'm actually writing an article about the heat recovery calculation estimation. Again, I'm not an expert in heat recovery, but I did my PhD in thermodynamics, so I kind of understand a little bit. But please, to the suppliers and to the manufacturers, don't claim 90% or efficiency more than 100%. So it's not possible. And when for everyone who is evaluating your system, please work on the cascade principle. Start your baseline with the demand, with the supply, see what you can do maximum on the demand side, and then go into the supply and check the electric baseline, the flow, the pressures, and the thermal recoveries. You can try this business case builder on Direktin.com. So you simply just need to go into our website, register here. Everything is for free. Then you will have your dashboard, and then basically once you click on your My Systems, you can start working, you can start registering your systems and see what are the possibilities for the savings will be. Or you can directly go into the business case builder and compressor room. This is also one of the tools. Compressor room helps you to establish the baseline for the business case builder. So you also can upload some information from some data loggers there. But if you're not so much into the compressor's power and everything, simply just use this and estimate what are the possibilities to do. And if you have more questions, feel free to reach out to us, and wish you a wonderful weekend, and see you next week into our another coffee and compressed air episode.